Hello everyone, welcome to the last video in my series on cellular respiration. So we are on part 4 of cellular respiration, and we're going to deal with the very last of the metabolic pathways, oxidative phosphorylation. So what we're going to discuss is really kind of two basic things. We want to kind of discuss the two pathways, what they are and where they happen, and then really how they work, how do they function, what do they do. So let's get started. Now, oxidative phosphorylation. This is an overarching term that is referencing two separate metabolic pathways. So when we say oxidative, we are saying that oxygen is required, and phosphorylation, we are saying that, remember that there will be a phosphate transferred to some place. Now, this is different than substrate level phosphorylation, but there are two separate pathways that this is composed of. One of these is called the electron transport chain. The electron transport chain. And a lot of times I'm just going to abbreviate it as the ETC, electron transport chain. And the other half of this major pathway is called chemiosmosis. And this is going to be the big one in terms of ATP production. So what I'm basically going to say is the electron transport chain will drive chemiosmosis, and that's really what I want to talk about. Now, we said, where does it actually occur? What is going on? Well, we already know the majority of the chemical reactions of cellular respiration in a eukaryotic cell happen in the mitochondria. And it's in the mitochondria, we know that these that there was an outer membrane and a highly folded inner membrane and a matrix. So we know there's a matrix inside here, an outer membrane, I'm just going to abbreviate it OM, and an inner membrane, I'm going to abbreviate it IM, and a space between the two called the intermembrane space. Now, the folds of the inner membrane were called the cristae. And it is on the cristae that majority of oxidative phosphorylation processes are going to occur, at least where the proteins will be embedded. And it's going to use these proteins to do some very interesting things. So we just need to recap that very quickly. Now, what I'm going to do to make this process understandable and simple is I generally just go through here and discuss this thing, and we'll do 1, 2, 3, 4, 5. Let's see. 1, 2, 3, 4, 5. 1, 2, 3. Good. And then we'll do this, and I'm going to draw a thing shaped like this. All right, it looks like a round bottom boiling flask, but that's not what it is. So let's imagine real quick, and I'm going to tell you what these things are first, but let's just set up an analogy to help you guys understand what's going on. Now, let's say we wanted to play a game of hot potato. Now, maybe you don't know what the game of hot potato is, basically, but basically what hot potato is, it's a game where we would take like a ball or anything, a potato, whatever you want to use, and you pass it around, and when the music stops, you're out. If you're holding the potato or whatever the thing is that you're using to stand in for a potato. But let's say we're going to play a real game of hot potato. And I go take a potato and I put it in the oven and I bake it, and it's hot, it's steamy, it will burn your skin. And then I take this hot potato and I throw it at one of you. And you grab this hot potato and you're like, oh, that's a very hot potato, it's burning my skin. So you throw it to the next person. And they grab it and they go, that's a hot potato, and they throw it to the next person. The next person gets it, goes, that's a pretty hot potato, and they get it and they throw it to the next person. The next person gets it, says, that's a warm potato. And by the time they throw it to enough people and they catch it, the last person that gets it goes, that's a cold potato. Now, what's happened with this very hot potato, when I threw it to you, you caught it in your hands, realized it was hot, got it away by throwing it to somebody else, and they catch it, and they realize it was pretty warm, and it got cooler each time. How is that? Well, what's happening is your hands will absorb some of the thermal energy that's found in the heated up, hot baked potato. Well, remember, back in my very first lecture in this series, I said that electrons are energy, and that we have these things called electron carriers that are like poker chips that I can cash in for money at a casino. Well, it's time to cash in our chips, guys, because this is what we are doing throughout this process, okay? We have electron carriers. So my stairs here that I've got, this represents the cristae of the mitochondria, okay? And the space under the stairs, this is the matrix. Always say that's the room of no requirement where Harry Potter sleeps. They're in the matrix of the mitochondria. And then up here we have our intermembrane space, okay, between the two membranes. Now, so that we now have these two things, what are these proteins, these little circles? These are the proteins of the electron transport chain, most of which are referred to as cytochromes. Cytochromes are these proteins that contain iron ions in them that have strong affinity for electrons. Now, let me just kind of explain this because this is pretty crucial to this thing functioning. Is at the top of the stairs, the first protein that's on top of my stairs here, it has the lowest affinity for electrons, where the one on the bottom has the highest affinity for electrons. And what's going to happen is these proteins will take turns shifting back and forth between reduced and oxidized and back to reduced, oxidized. They can go back and forth. Each one of them will be without an electron. They will be in their oxidized state. They will gain an electron, and then they will go back to having lost an electron. So they will start out as oxidized, they will get reduced, and they will become oxidized again. And as they go back and forth, the energy of that electron, like the heat of a hot potato, is absorbed by some of these proteins of the electron transport chains, these cytochromes, and they will use this energy to do something very interesting that I want to help you guys understand. Now, we said that in the last video, I said, okay, we have these molecules like NADH. And remember that NADH molecules, NAD, I cannot seem to make it want to draw, NADH, is carrying electrons and also hydrogen. So when the electron that it's dropping is passed off, what's going to happen? Let's say that this electron loses about 1/3 of the energy that it had to this first protein called a cytochrome. What is it going to do? Well, these cytochromes are going to take hydrogen ions that are found in the matrix, and they are going to pump it up into the inner membrane space. Okay? Now, there are others out here, others that are not referred to as cytochromes, like the second one in the line, which is CoQ, coenzyme Q. But what CoQ will do is it will grab this electron here, shuttle it to the next cytochrome, and here, again, another about 1/3 of the energy will be lost. Okay, so let's say I've got some more hydrogens down here, a lot of hydrogens in the matrix. This thing can pump it up here. And there's still some energy left in this electron, so this next, which is cytochrome C, will come in and move this electron. And then here, we're going to take it again, which 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Good. That our next one here will move it, and it will lose another 1/3 of its energy, roughly, at the 5th member of this complex. And again, what we're going to do is take these hydrogen ions and pump them up into the inner membrane space. And this is the role here of this molecule, is to take these electrons. Now, also in this complex, I'm going to go ahead and add this, is your FADH2 will add here. And its electrons will also do this as well. Okay? Now, what it's actually going to mean is that FADH produces less ATP, and I will show you why per molecule, and I'll show you guys why that is in a minute. Now, what happens here is this electron transport chain is producing no ATP. Now, what's going to happen is these electrons that I've done, they are pretty much very low energy. They're out of most of their energy or a lot of their energy, and it's kind of gone. But they need something to grab it up. And what they're going to use is a molecule called O2. O2 will grab up these molecules, oxygen. This is why we need oxygen. And this is why overall this process is called oxidative phosphorylation. Is this, we have these electrons come in. We call this the final electron acceptor. Now also, so our O2s, and what we're going to do with these O2s is we're going to take half of our O2 and we're going to actually take 2 hydrogen ions that we have around as well, and we are going to take these together and make the water that is made, metabolic water, from cellular respiration. So this is where our H2Os come from. But here's where I really want to make sure I take time to explain something, because we really have an opportunity here. Notice all these hydrogen ions here. We have now created in our inner membrane space basically a battery. We have now separated electrolytes. They are now separated. We basically have a fairly positive charge here and a fairly negative charge here. We also have it's fairly acidic here. And also we have this high hydrogen ion concentration. And this very high hydrogen ion concentration that I produced here generates something that we refer to as proton motive force. And this is emphasizing these high hydrogen ion concentrations' ability to do work. So what can happen is these high hydrogen ions, down here it is very low hydrogen ion now, because what a lot of the hydrogen ions, if they weren't pumped up, they got combined to make water, and the other ones got pumped up. So it's very low here, and we have the opportunity now with this concentration gradient difference and difference in charge. We have an electrochemical gradient that you might see in a battery. And in fact, we now know the mitochondria kind of works more like the Tesla batteries, where each of these folds act as separate cells that can each function independently, even when some get injured and damaged. Now, what I want to show you guys is there is a final protein that we need to know, and it's called ATP synthase. Now, ATP synthase does exactly what it tells you that it does. It does the job it says. It synthesizes ATP. Now, I have got molecules of ADP that a cell who is metabolically active will be phosphorylating it. It will take ATP, transfer the phosphates to something else, becoming ATP gets broken down into ADP, and this ADP is present very high amounts in a metabolically active cell. So what we can do is we can turn this like a turbine, kind of like a windmill or a turbine that's in a hydroelectric dam. To do that, we're going to take these hydrogen ions and they'll pass through this guy and they'll start to turn the turbine. And when it does, this thing makes a lot of ATP by basically turning this. There is basically, it is one of the smallest known molecular nanomotors out there, which is able to turn and catalyze by producing this ADP into ATP. And when the hydrogen ions pass through, this is called chemiosmosis. Let me go back to my blue marker here. This is our chemiosmosis. Chemiosmosis. And this is going to turn that ATP synthase nanomotor to produce a lot of ATP here for us, okay? And this is why if you don't have oxygen, you will die because your body cannot produce enough ATP. There is not enough ATP produced by the other processes that the body has. So what we have to do is use the electron transport chain to produce a proton motive force that can then drive chemiosmosis to make most of the ATP in our body. And you can produce about 34 to 36 molecules of ATP with this, where the others are together are only producing about 4 molecules of ATP. Now, FADH produces less because it's producing less of a proton motive force than is NADH. So NADH always gives you more bang for the buck. You always get a higher yield. That's always a question I ask on my exams. Which one produces the most ATP per turn? And that will be NADH because it gets more hydrogen ions produced. Theoretically, that's our big bang for the buck. So this is why I always like to say it's like a poker chip, because NADH is more valuable than FADH2. So guys, I hope this was useful and helpful, and this part here, the big part, it all puts it together. Always one of my favorite topics to teach in class is how does the body actually make energy? Metabolic pathways are crucial to understand because a lot of drugs, a lot of toxins, there are detergents that can disrupt the cristae. This is how some things like cyanide and things like that can kill us, is by disrupting electron transport chain. And a lot of drugs, that's what some of the toxins do. Some of the very fatal detergents and materials that you might ingest can disrupt these cell membranes and basically make it very difficult for the proton motive force to be generated. So I hope you found this series useful. I really enjoyed making it. Please let me know what you would like to see me do in future videos. And as always, don't forget to comment, like, and subscribe. But as always, thank you so much for watching my videos. I hope that I help you understand some complex things. And I'm just glad you're here. So thank you guys, and have a great day.